The final big idea today, folks, is the hydrophobic effect. And up on the right-hand side, I have the Gibbs free energy equation, delta G equals delta H minus T delta S. G is, of course, that's not how we spell energy. Let's try that again. Delta G is, of course, Gibbs free energy. Delta H, enthalpy, and delta S, entropy, with T being temp, which is a constant in this equation. So the hydrophobic effect, which is probably new to everyone, is the tendency of water to minimize its contact with hydrophobic molecules in order to increase its own entropy, the entropy of water. If you think about this, you have all experienced this in real life. When have you seen water not interacting well with things that are hydrophobic? If you said oil and vinegar, or oil and water, great, that's also the first thing that I think of, but there are, of course, other examples. So we're going to understand this idea in terms of Gibbs free energy, because really the hydrophobic effect comes down to the entropy of the solvent, which in biological things, biochemical examples largely is water. So let's take this step by step. Okay, we have two scenarios here. In the first scenario, shown here in the bottom left, I shake a bottle of oil and vinegar, salad dressing, to create an emulsion. An emulsion is a suspension of oil in water. And scenario 2, on the left-hand side, on the right-hand side, you carefully layer oil on top of a diluted vinegar solution. So all the oil is in a single layer, separated out from the water, compared to on the left-hand side, where little bits of oil are interspersed between the water. One of these two things is more favorable, and actually you know which one is more favorable, because if you make an emulsion like on the left, what happens if you let it sit for 10 minutes? You'll have the scenario here on the right, where the oil separates itself out from the water. Why does this happen? Really quick, I'm going to tell you the answer because you already heard the answer. They separate from each other to increase the entropy of water. Now let's kind of draw this out to understand it conceptually why this is true. So let's draw some oil and some water. So on the bottom here, I'm just going to draw oil in like little waves, and I'm going to label it oil because I don't really want to draw out a whole lipid right now. So there's your oil. Now let's imagine some water molecules interacting with this oil. I'm going to draw some various kind of orientations of the water. So here I've drawn 3 different orientations of water interacting with this oil. We should understand that the oil is very non-polar. It has no poles, so there really aren't any partial charges in a non-polar thing. Hopefully this is something that you recall way back from Gen Chem. But water, on the other hand, is very polar. Let's draw the dipole for all of these water molecules. So the dipole starting on the right-hand side would look like that, with the positive side facing the oil, the next water molecule would have the opposite type of dipole being drawn, with the negative side facing the oil. And the last water molecule is sideways, so neither of its dipoles are really pointing towards the oil. One of these scenarios is better than the others. So think big picture for a second. Like dissolves like, right? You know, kind of at a gut level, this is why oil and water don't mix. We need to go deeper than that in this course. We need to explain why they don't mix. Using like dissolves like, though, we can kind of choose the scenario here that is best. Let's start again all the way on the right-hand side. On the right-hand side, you have this partial. That is a terrible partial. Wow. Do better. Let's try this again. On the right-hand side, you have this partial positive directly pointing to the oil. This is no good because you have that partial charge right there facing the oil. Next to the left. Well, now it's not the partial positive, but it's the partial negative pointing right at that oil. That's no good. The oil's nonpolar. It will not interact well with something that has a partial negative. Finally, you have the water molecule on the left. Neither the partial positive nor the partial negative are directly pointing to the oil. So we don't have that charge interacting with a non-polar thing. They're kind of both slightly more away from the oil. This last one is going to be most favorable because the charged area isn't pointing directly at a non-polar area. So when water is interacting with oil, it will generally prefer this scenario on the left-hand side. The water won't want to rotate and look like this, because then the pole is right there by the oil. The water also won't want to rotate to look like this, because then the other pole is directing right towards the oil. So what you have is these water molecules against the oil that are kind of stuck in this orientation, not wanting to rotate, because if they rotate, their poles are pointed right at the nonpolar oil. So what we see here is water near the oil gets kind of stuck so that the dipoles don't directly interact. With the nonpolar oil. And so now I'm going to really quickly remind us of the definition of the hydrophobic effect so we can wrap up. So the hydrophobic effect is the tendency of water to minimize its interactions with hydrophobic molecules to increase its entropy. On this slide, I show you why water interacting with oil has low entropy, because the water molecule gets kind of stuck in this orientation. It can't rotate, it can't move around, therefore its entropy is low. So what happens, folks, is that emulsions become layers over time to decrease the interaction between water and oil. On the left-hand side, we have a large surface area of oil. So we have much more oil interacting with water if there's a large surface area. On the right-hand side, comparatively, we have a smaller surface area. So we have fewer water molecules interacting with the oil. And this wraps up our definition of the hydrophobic effect. So we've seen that water will minimize its contact with hydrophobic things. It will kind of go from an emulsion to one big clump of oil to minimize the interactions between water and oil. Why? In order to increase the entropy of water. If we have less surface area between the oil and the water, fewer molecules are going to be kind of stuck, unable to move. More water molecules are going to be able to roll around because they're not interacting with that oil. Therefore, the entropy of water is increased. And why do we even talk about the hydrophobic effect or Coulomb's law in the first place? Well, much of this course is devoted to talking about the interaction of biological molecules. And so, since many biomolecules are charged or partially charged, Coulomb's law is an important thing to start with so that we can always relate a new molecule back to something we already know. We'll see many biologically relevant examples of the hydrophobic effect. For example, we'll learn about lipids later on. They are nonpolar. This will be important to understanding their function. And finally, I want you to kind of walk away today understanding that the hydrophobic effect is really about the randomness of water. I know folks get really, honed into the idea that it's called the hydrophobic effect, so it's all about hydrophobicity. When it comes down to it, the hydrophobic effect is about water and the entropy of water. Okay, folks, great job making your way through my first series of videos. We talked about water and how it controls much of biochemistry. We talked a little bit about thermodynamics, bond energies, and hydration shells. We talked about Gibbs free energy and entropy when we discussed the hydrophobic effect. Coulomb's law and the hydrophobic effect are two of the most important topics that we will use all semester. You'll be able to use this thing that you've just learned now to understand a wide variety of things we learn later. So keep them in mind and learn them well now. With that, I'll see you in class, and I'll leave you with this cat meme with a cat in water. Thanks, everyone.